Hello and welcome to this tutorial on the PACE 2025 challenge. My name is Manuel and I hope to give you a practical introduction covering all aspects you need to get started with PACE very quickly. I will also introduce my Stride tool, which is designed to help you with common tasks while participating in PACE. It will help you stress test, benchmark your solver and visualize the solution. As a small disclaimer, I'm not directly involved with PACE and everything I say here are my own opinions. With that out of the way, let's get started. So, if you've never heard of PACE before, this is their website. It's an annual programming competition. Each year we have one or two hard optimization problems, and in the last years we had problems such as vertex cover, twin width, tree width, and so on. This year it covers two related problems, namely the dominating set and the hitting set problems. In a short while I will introduce the dominating set problem in more detail, and this is also the problem I will focus on today. So typically in PACE there are two tracks. In the so-called heuristic track, the goal is to find a somewhat good solution, and here typically the constraint is the running time. So you have a relatively short running time to process relatively large instances. And then there's the second track, the so-called exact track, where the goal is to find a best solution. As soon as you give a solution, it has to be optimal. And this year we actually have a new ruling that requires you to explain why you believe that your solver is optimal. So you are not asked to give a formal proof, but in theory somebody should be able to prove that your solver is optimal. And there is actually a nice phase during the end of the competition where you can look at the solvers of other teams and try to poke holes into their reasoning. Okay, so for each track, the organizers typically publish 100 problem instances ahead of time, and you can use them to develop your solver. This year, this is scheduled to happen in 2025. If you do not want to wait that long, just keep on watching. Stride will come to the rescue. Starting in April 2025, submissions via Optil.io are possible. This is a website where you can upload your solver, and then the website will execute your solver and publish the results on a scoring board. This is the scoring board of PACE from last year, and depending on the track, typically what you see here is the runtime or the solution quality in the heuristic track. Then in June 2025 you are asked to publish your solver source code and to submit it. So the organizers will have another 100 hidden instances, and the combination of these hidden instances and the public instances will be used to benchmark your final solver. Okay, so that's the gist of PACE. Let's come to this year's iteration. So as I already mentioned, today this year we have two problems, namely dominating set and hitting set, and I'm gonna cover the dominating set. So the task is quite simple. We are given a graph, and then our job is to find a so-called dominating set. A dominating set is a subset of nodes such that for each node, let's pick one, either the node itself is in the subset, this is not the case here, or a neighbor of it is in the subset. This is the case. And if you check this for all nodes over here, this constraint is satisfied, and therefore 3 and 5 are a so-called dominating set. And in fact, it's quite easy to see that in this case there's no dominating set of size 1, and so this is a smallest dominating set. And this would be a valid answer in the exact track. In the heuristic track, it would have been also okay to, for instance, also include the 2 over here. But how do we participate? We have to implement a solver, and this needs to understand the file format. So graphs are given in this Dimex format. It includes comments, a header, and then a list of edges. Now switch over to my IDE to show you more details. Let's try to build this graph over here. So we have a star graph with the center node 4 and the satellites 1, 2 and 3. So recall, the first non-comment line has to be the header, which starts with a P, then the problem name, dominating set. Then comes the number of nodes, that's 4 in this case, and we have 3 edges. So that is the header line. We are now free to add another comment or something like that. And then we have to eventually add all our edges. So the first edge could be between node 1 and 4, the second one between 2 and 4, and the last one between 3 and 4. And that's it. That's our graph. Now the next thing we have to understand is how we can give this graph to our solver. And PACE requires us to use pipes for that. So in Linux I can use cat to print out the contents of a file, but I can also pipe this, for instance, into the tool word count and get the number of lines. And in this fashion we are supposed to input the graph to our solver. And so in the next step, let's implement the I/O module of the solver. And for this I use the module PACE.io. So in PACE.io I will implement 2 functions, namely readGraph and reportDOM.set. So this is the input, this is the output. And the idea is basically that we read the graph, then we compute some dominating set and eventually report it. The way to read the input is to iterate over the so-called standard input. This is the pipe through which our solver receives the input instances. And in Python that's quite easy to do. We simply iterate over all lines in sys.stdin. And to start with, let's just print it. So if I execute this now, we get something odd. We get each line of the input file separated by an empty line. And this is simply because if I iterate through stdin, the line breaks and such are not removed. But we can do this quite easily. We simply use line.strip. If I now execute this program again, this is exactly what is supposed to happen. So now let's parse the file. The first thing that can happen is that we see an empty line, or that our line starts with a C and therefore is a comment. And we can check this quite easily. And if we observe such a line, we simply skip over it. The second option that we can have is that our line starts with a PDS. So we have a header line for our specific problem here. And in this case, we want to pass the number of nodes and number of edges. And there are multiple ways to do this. A quite straightforward one is we assume that the input is formatted in a legal way. Then we can simply ask Python to split the line, add white spaces, and unpack all the arguments. And we are interested in n and m. So n is the number of nodes, m is the number of edges. So in Python, n and m are currently strings, and we cannot compute with strings directly, so we have to cast them into integers, and we can do this way. Then we are done, and we can continue. If we reach this point in our execution, we made sure that we have not a comment line and we have not a header line, so the only thing that remains is an edge. And I can again unpack, split my line and unpack it. And I again have to convert the nodes into integers. Okay. And the data structure I want to build is an adjacency list, which is simply a list which contains another list for each node. So if our graph has 3 nodes, it contains 3 lists, and the ith entry stores all the neighbors of node I. So in this case, node 1 is a neighbor of node 0 and has a self loop. Okay, that's the structure we want to build. So in order to build it, we need to know how many elements we need. So at this point, I can build an adjacency list, and we can use list comprehensions to do this. So for each node u in range from 1 to n plus 1, I need to build a neighborhood, and for this I use the data structure set. So why 1 to n plus 1? This is simply because in PACE the first node starts with a 1, and in Python the last entry of range is exclusive. So this range function will iterate through all numbers from 1 to n including. There's a small trick I can do, simply because Python starts counting from 0, but we only have nodes starting in 1. Let's add a dummy element here, which makes sure that if we access the 0th entry of our adjacency list, we get this dummy element. Okay, so nice. Now we have an empty adjacency list. What remains to do is to insert the edges we observe. And this is quite easy. So if we have an edge from u to v, we only go to u and add node v, and vice versa. We go to v and add node u, returning our adjacency list. There's another small hack I'm gonna do. So for the dominating set, it is often very helpful that a node has itself as a neighbor. And so I simply add this here. So if I look at the main, I implemented something like read this adjacency list. And what I'm gonna do is now output this adjacency list. And this is exactly the result we expected. We start with our dummy element at position 0. At position 1 we have the neighbors of node 1. This is the node itself, and the true neighbor 4, and so on. Let me put the whole function here so that you can look at it again. Okay, what remains to do is to produce a valid dominating set. So the most stupid way we can do is simply put each node into the dominating set. And let's do this. So we can simply do this by iterating from 1 to the size of our adjacency list. Okay, now we have a huge dominating set. What needs to be done is we have to report it. And here PACE requires us to start the first line with the size of the dominating set. And then simply for each node in the dominating set, we add another line which only contains the node. If I now execute this program, it should be a valid solver. So what do we expect as a result? The first line is supposed to be a 4, because our dominating set for this particular graph has 4 nodes, and then we expect all nodes to be listed. This is exactly what happens here. So the cardinality is 4, and then we observe all the nodes. We still have the slight issue that the first line contains syntactically incorrect garbage, but we can fix this quite easily. We are also allowed to add comments to our output if they start with a C. And now we actually have a solver which produces a dominating set. Obviously, this is not the dominating set we are after, because this is way too large. And so let's start with a very naive way to solve dominating set, a little bit more clever, but only a little bit. This starts by importing the 2 functions we just implemented. The way I want to approach this problem is I want to maintain a second data structure, which I called covered. And this simply stores all the nodes for which we don't have to fulfill additional constraints. So recall, a subset of nodes is a valid dominating set if each node is either directly in the dominating set or has one of its neighbors in the dominating set. So for the graph 1, 2, 3, it would suffice to put the node 2 into it, simply because this will also cover node 1 and 3. And this is the idea of the algorithm. So let's iterate over all nodes and simply check if the node is already covered. If this is the case, we have nothing left to do. If this is not the case, let's simply put the node in the dominating set and cover all its neighbors. And this is what the update function does. The update function computes the union of covered and the neighborhood of U and assigns this to covered. So if I execute this algorithm on our input graph, what happens? We start with the first node, put it into the dominating set. This covers node 1 and 4. Then we take the second node. This is not yet covered, so we put it in. And the third node is also not covered, so we put it in also. So if I run this program, what we expect to see is the first line should be a 3, because we expect a dominating set of size 3, and then the nodes 1, 2, and 3 should be listed. Let's see whether this actually happens. Yes. So this implementation is a little bit better. We reduced our dominating set size from 4 to 3. But looking at the graph again, this is obviously not the right answer, because if we put in the node 4, this would be a much better choice, because 4 covers everybody else. And so this is the main idea of the greedy algorithm. So the greedy algorithm is iterative, and at each round it checks whether it already produced a dominating set so that all nodes are covered. If it reached this point, it simply stops. Otherwise, it searches a node which maximizes the gain, which means that it covers the largest number of nodes currently possible. The first thing we have to do is, again, define the data structure covered, and we repeat this algorithm as long as we have not covered all nodes. Recall that our adjacency list starts with our dummy element, so we actually have to add a 1 here. So the next thing that we do is we iterate over all nodes, and we look at their respective neighborhoods and remove all the nodes which are already covered. And then we count how many nodes remain, and this is what we call the gain of the node. And now we are looking for a node which maximizes the gain. Obviously in Python there are nice ways to do this, but let's be a little bit more explicit and do this by hand. So the max gain is initially 0, and the argmax, this is the node with the largest gain, is initially none. And what we do is, if the gain we just computed is larger than our max gain known so far, we update the max gain and we say that our argmax is node u. And in the end, we check that argmax is not none. Now we know a node with the largest gain, and we simply add this to the dominating set as before. And we again need to update covered with the neighborhood of argmax. Looking at this graph again, what will happen? So the largest gain is node 4. This will be added, and in this case, the solver by chance finds an optimal solution. Or in this particular case, the optimal solution. We can run greedy, and we get exactly what we expect. The cardinality is 1, and the only node in the solution is 4. It is pretty easy to show that this algorithm is not optimal in every case. And I leave it up to you to find an example. Actually, we know that it has an approximation factor which is logarithmic in the number of nodes, so it's not too bad, but what I can already tell you in practice, it's relatively easy to beat greedy. I want to show you one example which also introduces a new technique which is important for PACE. So, what's the difference between greedy and the naive algorithm we just implemented? If you look at them side by side, the main difference is that in the naive algorithm we have a fixed order in which we go through the nodes and add them one by one if they are not yet covered. While in greedy, we try to find a best guess and add this. Sometimes this guess is good, sometimes it isn't. Let's try a completely different approach in which we actually guess by random choice the order in which we consider nodes. Instead of going through the nodes one by one, we take a list of this range, then we import random. We shuffle the order randomly. So this is now a random permutation. And let's try to run this program. So again, I have to make it executable. So in this case, we were lucky. We started with node 4. That's all fine. In this case, we were unlucky because we started with a node different than 4. And we are unlucky quite frequently. What can we do? An easy choice is to repeat this process. So let's put everything here in a function. And let's simply repeat this 100 times. And we start with some solution. And if the new candidate is smaller than the solution so far, we take it as our new norm set. So if I run this algorithm, in this particular case, it's quite likely that out of these 100 attempts, I will find the correct order. So in general, this algorithm unfortunately does not scale well. Now the question is, how many attempts can we afford to do? And in general, the answer is, well, that depends on the graph, because the larger the graph, the longer the computation time per iteration, and we have this time limit of 5 minutes or so during the competition, so we have to stop at some point before the time runs out. This is the actual reason why I'm showing you this algorithm, because I want to explain to you how the timeout procedure works in PACE. So, many heuristic solvers in PACE use the following idea. They come up with an initial solution, something like greedy, and then try to iteratively improve the solution. And they repeat this until they are informed by the environment that they now run out of time. And the way this is done is using a sig term. So typically the sig term comes after roughly 5 minutes. And then you have a so-called grace period of a couple of seconds. And within this grace period, you are supposed to report the best solution you found so far, and then terminate. If you manage to do this, the solution will be accepted. Otherwise, after the grace period, a sig kill will arrive, which simply terminates your program, and then you cannot report anymore. So in order to implement this, we need the signal package. And the rough idea is that we can use the signal method within and ask it to respond to a sig term which arrives by calling some handler. A handler is nothing else than an ordinary function which takes 2 parameters, which I'm going to ignore here. So usually the recommendation is to do as little work in the signal handler as possible, and especially don't use print or something like that, because in some programming languages this can lead to deadlocks. So what we rather do is we use a variable that in this case is called keep running, and we initialize this with true, and once we reach this handler, we set it to false. And that's it. This is how we interact with the environment. Now we have to actually use keep running, and the only modification we need is, rather than prescribing a certain number of attempts, simply do it until keep running goes to false. Let's execute the solver. Obviously this does not terminate, so we have to send it a sig term, and one way to do it under Linux is to use a kill all Python. And then the output is produced. To sum up, what did we do? We implemented our input and output functions. We implemented a very naive solver, then implemented greedy, and now a randomization of the naive algorithm with which we showcased how signal handling works. And by the way, the same signal handling can be used in different programming languages. Now the question is, which of these implementations is better? I think it's quite easy to see that naive will lose the game, but to me, at the moment, it's not clear whether greedy or naive random is the better choice. And obviously the answer depends on the input instances. So what we need to do now is take all the inputs and run our solver against it. Unfortunately, at the time of the recording, the instances are not yet available, and even if they were, we needed another program to run all these simulations. This is where the Stride tool comes in. So the Stride tool is a website which at the moment contains almost 70,000 instances, for which we already computed some dominating sets. So my expectation is that roughly 2/3 of the instances here are solved optimally. The remainder is only solved heuristically or solved not at all. So if you look here, some of them are not solved. This is where the community comes in. My hope is that over the time, you and other people will use this tool to evaluate your solvers and upload the solutions. Let me first show you a couple of features of this website. So what you can do, for instance, is you can add constraints. Let's say initially you're not comfortable to work on large instances. So let's say we don't want anything with more than 20 nodes, or you want to have at least 10 nodes, something like that. Maybe sort them by ID. And you can sort them by additional constraints. For instance, the degrees, the connected components, the tree width. You can select by planarity or bipartiteness, all these things. So what you can do then, once you have selected a graph, is you can download it. That's exactly in the Dimax format I explained earlier. Or you can visualize it. So in this case we have our Patterson graph, which is not that easy to see here, but if you squint a little bit, maybe you recognize it. I will come back to this visualization a little bit later, because there are more features that I want to discuss. So obviously, it's not a good idea to click download on 70,000 instances, and this is where the runner comes into place. So the runner is a small tool which allows you to invoke your solver on a predefined set of instances. It will take advantage of the parallelism of your machine, so it will start a solver per core, it will check the solution afterwards, and it will compare the size to the sizes that are already known, and if you found a better solution, it will upload it to the website. So if you're working under Linux, you can simply navigate to the latest build and download a statically linked binary. What I want to show you now is how you can build it. So the only dependency we have is you need to have Rust installed, and this is less dramatic as it sounds. So if you go to the Rust website, you simply have to execute this one line on your shell, and this will install Rust. Once you've done this, you can come back and you can simply check out the sources by using git clone and the URL. Once you've done this, you navigate into the directory, and all that remains to do is to build it. So this takes a couple of seconds. Okay, once it is done, you can copy the runner out of the directory. And this is only for convenience. You can also leave the binary there. And let's get back into the directory where we just implemented our solvers. The first thing you have to do is you have to update the runner. What this will do is it will contact the server and download a summary of all instance data available, as well as a set of small graphs. This is simply to reduce the overheads. So the first download will be like 150 megabytes. So if I now run it again, it only updates the metadata. My recommendation is to run update from time to time, let's say once a day or so. Once this is done, you can use the runner to invoke your solver. And there are multiple ways. One way, for instance, is to go again to the website, select the graphs you want, click download, and then you get a file. Let me choose a very small instance. I'm only selecting graphs which have exactly 100 nodes, and I download this list. So then I can come back and copy this list over here. So now we have our demo list here, and then I can use the runner with the run command, instructed to use the list and to use the solver, let's say greedy, and to run it. So we executed roughly 150 instances, of which 108 were solved optimally, a couple of which were solved suboptimally. So if you would want to participate in the heuristic track, this is okay. If this is supposed to be an optimal solver, obviously this would be a problem because it produced suboptimal results. So there is a second feature of the runner that I want to show to you. In order to use this, we have to register our solver. And this is pretty easy. You simply execute runner register once. And the only thing that it is doing, it stores a random UUID in your config file. So there is a config file stored in stride config.json, where you can pre-select certain parameters, so defaults for timeouts and graces and number of parallel jobs and so on. And one important feature is the solver UUID. So by default, no UUID is stored here, and so all uploads will be anonymously. Once you call register, all uploads will be associated to the solver ID. So if you want to unregister, the only thing you have to do is you delete your config file or you remove the UUID by hand. But since I actually want to show you how to use it, let's re-register. And now we can invoke the runner. This time I use a different method to select the instances we want to target. What we do now is we invoke the runner, again with run, and we can also issue an SQL query against our local copy of the metadata. So if you happen to accidentally have a drop table in there, you will only affect your local data, and if this should happen to you, simply run runner update and everything should be cleaned up again. So in this case, let's say we want to have at most, I don't know, 40 nodes and at most 80 edges, and we want to execute greedy. So these were a lot of instances, but we managed to compute them in roughly under 50 seconds on my machine. So the next thing we can do is we want to execute our naive random implementation. And to do this, we need to establish a time limit. And let's say we're interested in a time limit of 1 second. So what happens now is the solver is started, and here you see the progress with the time limit and the grace period. By default, the grace period is 5 seconds, so it is rather large here. Okay, now that this is done, we can visit the website. And as you can see, the URL includes our unique UUID. So let's visit this. And so what we see here is a log over the uploads. Simply to make it a little bit easier, let's give this a name. This was greedy. This one is the second one, so this was randomized. Timeout was 1 second. And what we see is obviously that greedy is faster most of the time. So this tells us the instances, this tells us the runtime. So on the x-axis we have the instances, on the y-axis we have the runtime. But for the heuristic track, this is not so interesting. We are more interested in the quality. And so maybe this plot needs a little bit of explanation. So what we do is for each instance that a solver solved is that we compute the ratio between the solution size and the best known size. So this ratio will always be at least 1, and the worse a solution is, the larger the number is. And what we do next is we sort this number for each solver. And so the goal of a good solver is to stay down at the bottom as long as possible and then rise only very slowly. And so we see greedy does this better than the randomized one over here. You can also inspect the runs in more detail. Simply click on the name, and then one option, for instance, is to sort by the score difference. So the difference between the solution your solver produced and the best known. If we then click on the magnifying glass, we actually get a visualization. So in blue are all the nodes which are in the DOM set, and you can see the problem over here. So in this case it would have been way better to put in the 19 rather than the guys over here. Green are covered nodes, and yellow are nodes which are covered by multiple neighbors. So as you can see here, these are typically the nodes where you might optimize something. You can also select between the different runs you did. And in this case, greedy was way better than the randomized solution because it chose the hubs in the middle. And so you maybe have a way to understand your problems better. Obviously, this does not really work for large instances, but maybe it's a nice addition to your pipeline. So this brings me to a conclusion. I hope that you now have all the tools available to successfully participate in the PACE challenge. It would really mean a lot to me if you chose to use the Stride Runner and also upload your solutions. And by the way, if you look at the repository of the Stride Runner, there's also a greedy implementation in Rust. So if you wanted to use a different language than Python. And with that, I wish you all the best and have fun participating at PACE. Thank you.